Okay, so welcome back to this next video in which we are discussing the RAS, RAF, MEK, ERK pathway. Okay, right. So we've just been discussing the farnesylation of the RAS monomeric G proteins. Okay, so I'm now going to take you back to this piece of paper here. Okay, so we've just been discussing this lipid moiety that we've had attached onto our RAS monomeric G protein, which is attaching it to the underside of the phospholipid bilayer. Okay, we now want to see the role of the SOS protein in activating the monomeric G protein. So, remember, let me just remind you that once we've got the activation of the receptor tyrosine kinases, what will happen is you'll get the docking of this growth factor receptor binding protein 2, GRB2, onto phosphotyrosine residues on the intracellular aspect of the receptor tyrosine kinase dimer here. Okay, then what will happen is GRB2 also has this SH3 domain, which will bind to the proline-rich region of this son of severness protein. The son of severness protein is now going to catalyze the activation of the RAS monomeric G protein. Okay, so it will bind to the RAS monomeric G protein. That will allow the RAS monomeric G protein to give up the guanosine diphosphate it has bound to it, and instead a molecule of guanosine triphosphate will bind in there. Okay, and then that activated RAS monomeric G protein will cleave away from the son of severness protein. So let me draw this all out for you. Okay, right. So let's draw our receptor tyrosine kinase once again. It's all good revision. Okay, so here is our amino group. Okay, then we've got our ligand binding domain extracellularly, and this is bound to the ligand here. Then we've got our membrane-spanning alpha helix, and then our tyrosine kinase domain on the intracellular aspect, and then our C-terminal tail here. Okay, right. So this is then dimerized with another receptor tyrosine kinase, which is most likely the same receptor tyrosine kinase, or at least one, remember, that's in the same family of receptor tyrosine kinases as the first one. Then we've got our membrane-spanning alpha helix. Then we've also got another tyrosine kinase domain intracellularly, and here is our carboxylic acid terminus here. Okay, so colour in the tyrosine kinase domains in blue here. Okay, then we've got our membrane-spanning alpha helices in red here. Okay, then our ligand binding domains extracellularly here in orange, which are dimerized together. And then we've got the ligand bound to those ligand binding domains here in turquoise. Okay, then of course what happens is that brings the two tyrosine kinase domains close to each other. They phosphorylate one another. Okay, and these phosphate groups which are added onto tyrosine residues, what else? Okay, then activate the tyrosine kinase domain, so they're now more active, and they then proceed to phosphorylate the surrounding tyrosine residues. So this tyrosine kinase domain will be responsible for the phosphate groups added onto the tyrosine residues of this second receptor tyrosine kinase, whilst this activated tyrosine kinase domain on the second receptor tyrosine kinase will be responsible for the phosphorylation of the tyrosine residues on the cytoplasmic tail of the first receptor tyrosine kinase. Okay, so I'll colour these in once again in pink here. Okay, now, what then is going to happen is we'll get the growth factor receptor binding protein 2, which has this special SH2 domain for binding to phosphotyrosine residues. This will bind onto a phosphotyrosine residue here. So remember, this is the SH2 domain, and then we've also got a special domain known as the SH3 domain, which will then bind to the proline-rich region of the SOS protein. So here is our son of severness protein with that special proline-rich region, which I'll colour in vivid purple here. Okay, and then I'll colour in the rest of son of severness in yellow. Okay, so all of this is the rest of son of severness. Right. Okay, so then we've also got to label up our growth factor receptor binding protein 2, our GRB2 here. Okay, and that's got those two special domains, the SH2 domain here in green, and then the SH3 domain, which is bound to the proline-rich region in the son of severness protein here. Okay, now this is going to bind to our inactivated RAS monomeric G protein. So this is the new bit coming now. Okay, so here it is, and then we've got our lipid moiety on the RAS monomeric G protein, which is one of these farnesyl groups here. Okay, and this could be any one of those 4 RAS monomeric G proteins that we discussed: BRAS, NRAS, KRAS4A, and KRAS4B. Okay, right. Now, when the monomeric RAS G protein originally bound, it was in the off state, it had guanosine diphosphate bound to it. Now what's going to happen is when the SOS binds to the RAS, okay, this makes this interaction between the RAS and the GDP much less strong. Okay, so initially it was a very, very tight bond. The GDP was not going to leave the RAS initially. Okay, there was not a chance that the RAS would activate itself spontaneously. Okay, but once it binds to SOS, this interaction becomes much weaker and the guanosine diphosphate can now leave. And then what happens is a molecule of guanosine triphosphate will come in and replace that molecule of guanosine diphosphate. Then, when the GTP binds here, it changes the conformation of the RAS monomeric G protein, and it will now cleave away from the SOS. Okay, so it'll go off on its own little adventure. And now we've got this activated RAS monomeric G protein that is on the underside of the phospholipid bilayer. So here it is. We've got our RAS protein, and now it's got guanosine triphosphate bound to it, and is therefore in the on state. So this is RAS here. Okay, and this now is going to activate the next member along in this great pathway. Okay, and of course the son of 7-less protein can now go on and activate more RAS monomeric G proteins. Okay, right. So we now want to discuss what RAS is going to activate. Okay, it's going to activate a kinase enzyme known as RAF. Okay, so now we're on to the next molecule in our title. So remember, our title was RAS, RAF, MEK, ERK. Okay, so we've seen RAS now. The next one is RAF. Okay, so RAF is a kinase enzyme that is initially inactive and sits in the cytoplasm. Okay, so here is our RAF kinase enzyme that will be sitting within the cytoplasm. So it's not bound to the underside of the phospholipid bilayer like RAS is. It's just floating around in the cytoplasm. Okay, so we'll colour in RAF in orange. Now, just as there was more than one RAS protein, there was more than one RAF kinase protein. Okay, in fact, there are actually 3 RAF kinase enzymes. Now, the same is true for RAF as was true for RAS, which is that we don't need to hugely worry about the difference between these 3 RAFs. Okay, but I will give you the names of the 3 different RAFs just in case you come across it. So, there is A RAF, okay, there is then B RAF, and there is also C RAF. Now, CRAF is also called RAF1, so if you see RAF1, it's probably the more common terminology for CRAF than CRAF. So, RAF1 or CRAF, they're the same thing. Okay, so these are the 3 different RAF enzymes. Okay, and currently they are all sitting in the cytoplasm inactive, but they can be activated by RAS monomeric G proteins. Now, in the inactive state, what they have is a number of phosphate groups that are on inhibitory phosphorylation sites. So RAF has a huge number of phosphorylation sites. It has a huge number of residues which are capable of being phosphorylated. Some of these are inhibitory phosphorylation sites and some of them are excitatory phosphorylation sites. When it's initially inactive, it will have the inhibitory phosphorylation sites phosphorylated. This is what these phosphate groups here represent. These are the inhibitory phosphate groups, okay? So they're on inhibitory phosphorylation sites. So I'll just put some sort of arrow here. So these are inhibitory phosphorylation sites here. Okay, now, what are these inhibitory phosphate groups that we have on these inhibitory, oh dear, how is this going to fit in? No, phosphorylation sites. What are they going to do? Okay, well, once you've got these inhibitory phosphorylations on you, what can happen is another protein can come and bind to our RAF kinase enzyme, and indeed it does come and bind, okay, to the inactive enzyme, and this protein is called 14-3-3. Okay, so I'm not going to colour that in turquoise. What colour should I have? I'll have it in pink. Okay, so here in pink we have our 14-3-3 protein, which will bind to these RAF kinase enzymes when they have the inhibitory phosphate groups on. And all of this keeps our RAF enzyme nicely inhibited. Now, once we've got on-RAS proteins, so once we've got RAS proteins which have guanosine triphosphate bound to them, okay, what can happen is these RAF kinases that are inactive, they can come and bind to the RAS enzymes, well, the RAS proteins that are active here. Okay, so here comes our RAF kinase enzyme, whether it's ARAF, BRAF, or CRAF. It's going to come and bind to our RAS protein that's in the on state. Okay, now this doesn't initially activate it. It does do two things, however. It brings it, firstly, to the underside of the phospholipid bilayer, so it changes the localization of this RAF kinase enzyme. And in addition, what it also does is it will cause conformational changes, but these conformational changes are not enough to activate RAF on their own. Okay, we're going to need further stages to activate the RAF, because at the moment we still have these inhibitory phosphate groups on us, and we still have this silly 14-3-3 protein attached as well. Okay, so we need to certainly get rid of those before we can do anything. So, now that we've localized it at the underside of the phospholipid bilayer, and also now that we have changed its conformation a little bit, what can now happen is an enzyme can come in and remove these inhibitory phosphorylations on the RAF kinase, and thereby remove this 14-3-3 protein here, because remember, that protein can only bind once you've got these inhibitory phosphorylations, shown here in vivid purple. Okay, so what's now going to happen is an enzyme is going to come along and cleave off those inhibitory phosphate groups here. Okay, and when you cleave off those inhibitory phosphate groups, the 14-3-3 protein goes as well. So what is this protein called? Well, it's called PP2A. Okay, now what does PP2A stand for? It stands for protein phosphatase 2A. Okay, so a phosphatase is an enzyme which removes phosphate groups. Just as a kinase enzyme puts phosphate groups on, a phosphatase enzyme takes phosphate groups off. Okay, so this little enzyme that I'm now outlining in bright green here, this is protein phosphatase 2A, and it's going to get rid of those phosphate groups that are on the inhibitory phosphorylation sites of our RAF kinase enzyme. That will cause the 14-3-3 protein to go, so we can say goodbye to that. Now, it's not over there. That doesn't yet fully activate the RAF kinase enzyme. So we're going to take this further. Okay, so once protein phosphatase 2A has taken off the inhibitory phosphate groups, we're now going to stick phosphate groups onto the excitatory phosphorylation sites. Okay, so what's now going to come along is a tyrosine kinase enzyme, which is going to phosphorylate tyrosine residues which form the excitatory phosphorylation sites of our RAF kinase enzyme. Okay, and this tyrosine kinase enzyme here, which is one of these tyrosine kinase enzymes that is free within the cytoplasm, is, as promised, a SARC family tyrosine kinase enzyme. Okay, so I'll colour in this SARC family tyrosine kinase enzyme in turquoise here. Okay, so this is going to now come in and phosphorylate certain residues on our RAF kinase enzyme, and this then is going to activate our RAF kinase enzyme. So let's draw this. So, if we've got our phospholipid bilayer here, we know we've got our RAS monomeric G protein that's currently in the on state, which is attached to the underside of the phospholipid bilayer still by this farnesyl group. Okay, so here is our RAS monomeric G protein, either BRAS, NRAS, KRAS4A, or KRAS4B, they all do it. Okay, now what's going to happen is we know that our RAF kinase enzyme has come from the cytoplasm and bound onto our RAS protein here, okay, which means that it's now also localized at the underside of the phospholipid bilayer. What then has happened is the protein phosphatase 2A has taken off these inhibitory phosphate groups, and that means that the 14-free protein is no longer attached to our RAF kinase enzyme, which is here in green. Okay, and now what's going to happen is our SARC family tyrosine kinase is going to come along, which I'll draw here, and it's going to phosphorylate certain phosphorylation sites which are excitatory. So let's say we've got an excitatory phosphorylation site here, and of course this is going to be a tyrosine residue that forms this phosphorylation site, because this SARC family enzyme is a tyrosine kinase. Okay, so this is an example of a tyrosine kinase that is free within the cytoplasm rather than being part of the cytoplasmic tail of a receptor tyrosine kinase. Okay, this now activates our RAF kinase enzyme. So this is now activated. Now, what is it once it's activated? Well, RAF kinase enzymes are serine-threonine kinases, so they're not tyrosine kinases. They instead phosphorylate serine and threonine residues within proteins rather than tyrosine residues. So let me just remind you of the structure of a serine and a threonine residue. So we'll start with a serine residue then. So here's the amino group. Again, I'm drawing it as though it's involved in a peptide link, so I'm drawing a residue rather than the free amino acid. Then we've got our alpha carbon with a hydrogen coming off. Then we've got our carboxylic acid group, so that's the core amino acid residue structure. And then the R group of a serine residue consists of a methylene group, then with an alcohol group coming off. Okay, so this is a serine residue. Okay, now let's see threonine, which is almost identical to serine. So once again, we'll draw the core amino acid structure here. So the amino group, the alpha carbon with the hydrogen coming off, the carboxylic acid group. Okay, now we have a carbon with an alcohol group coming off, just like in serine, and we still have one hydrogen coming off it as well. But then instead of having a second hydrogen, we have a methyl group coming off this carbon instead of a second hydrogen. Okay, so this is the structure of a threonine residue. Okay, right. So these are these two residues that are going to be phosphorylated by serine-threonine kinase enzymes. Okay, so we're going to add a phosphate group onto these, so you can hopefully see that they're almost identical. So I'll show you phosphorylation like I showed you for tyrosine residues, just to remind you. So we've got a phosphate group firstly, so here's a phosphorus atom, double bound to an oxygen atom. It will have two alcohol groups coming off it, and then a single bond to an oxygen, which this has then acquired an extra electron via ionic means and therefore has a negative charge on that oxygen. Okay, right. So again, I will show you the basic principle of what we're doing. In reality, of course, these serine-threonine kinase enzymes will not add on inorganic phosphate groups onto serine and threonine residues. Instead, they'll take the phosphate group off the ATP molecules and add that on, returning the ATP molecule down to being an ADP molecule. Okay, so how are we then going to add this phosphate group onto this alcohol group of our serine or threonine residue? Well, again, we're going to form a phosphoester link. So we're going to take the alcohol group off the phosphate group. We're going to take the hydrogen off the alcohol group of the serine or threonine residue, and we're then going to attach the oxygen of the serine-threonine residue to the phosphorus atom of the phosphate group, and that link there, which creates as a phosphorylated serine residue, this is a phosphoester link. Okay, showing its parallels with ester links between carboxylic acid groups and alcohol groups. Okay, so this is a phosphoester link. Right, so once we've got this activated RAF enzyme, it's a serine-threonine kinase, so it adds phosphate groups onto serine and threonine residues within proteins. So what is the target then of our RAF enzyme? Okay, well, the next enzyme in this cascade we know because it's within the title. The next enzyme is going to be something called MEK. Okay, so let me draw MEK down here. Okay, and this too is a kinase enzyme. Okay, it's a slightly fancier kinase enzyme than anything we've seen yet, which I'll discuss in a moment. Okay, so this is MEK. So I'll colour in MEK in red here. Okay, so firstly, what does MEK stand for? Well, MEK stands for the mitogen activated protein kinase, extracellular signal regulated kinase. Okay, now that can be shortened down a little bit. So what it stands for is the MAP kinase / ERK kinase. Okay, so basically this enzyme, MEK, is going to phosphorylate another enzyme that's the next one along, which we're about to come to. So we're getting a little bit ahead of ourselves, but I'll draw this now. Okay, so this is about to phosphorylate the next enzyme along, and this next enzyme along is called MAP kinase, MAPK, or it's also called ERK for extracellular signal regulated kinase. Okay, I'll talk about that again in a moment. So this is going to phosphorylate this next one, and therefore it's the kinase of this. So that's where the name MEK comes from. You take the M from MAPK, okay, so that's the M there. You take the E from ERK, okay, and then the K from kinase, and that gives you MEK. Okay, right. So there are two forms of MEK. There is MEK1 and MEK2. Again, as always, they pretty much do the same thing as far as we're concerned, so we're not going to differentiate between them, and we'll just call this enzyme a MEK enzyme, but be aware that I mean it could be either a MEK1 enzyme or it could be a MEK2 enzyme. Okay, right. So, what then is going to happen? Well, basically, the RAF kinase, which is now activated, we know is a serine-threonine kinase. Okay, so what's going to happen is RAF is going to phosphorylate some serine residues which are within the active site, which by the way is this little invagination that I'm drawing here. Okay, it's going to phosphorylate some serine residues within the active site of our MEK enzyme. Okay, so these are serine residues that we are phosphorylating here. And when you phosphorylate these serine residues, that will turn the MEK enzyme on, okay? So it's now going to become active, and it remains in the cytoplasm. So it will go up and see the RAF kinase, which will then phosphorylate its serine residues, and then it's remaining in the cytoplasm, but it's now active, okay? And it's going to phosphorylate the next enzyme along. Okay, now, what type of a kinase enzyme then is MEK? So I said it was a little bit more fancy than anything else we've seen so far, and it is. It's actually a kinase enzyme for all three of the residues that we've seen so far. So it's actually a tyrosine and a serine-threonine kinase. And for short, serine and threonine are abbreviated to SER for serine and threonine THR. Okay, so it's a tyrosine and a serine-threonine kinase. So it's capable of phosphorylating not only tyrosine residues, but also serine and threonine residues. So it's quite fancy. Okay, right. So that's MEK now. And what's going to happen now is that MEK is going to phosphorylate this next enzyme along, which has these two names. So let's discuss these full names now. So we'll start with MAPK. So what does MAPK stand for? This stands for mitogen activated. Okay, that's the MA. P is for protein, and then the K is for kinase. So that's what MAPK stands for. Now, people often just abbreviate the mitogen activated protein to MAP. Okay, so often people will call these enzymes the MAP kinase enzymes. Okay, so that's what the MAPK is short for, MAP kinase. ERK then. And what does ERK stand for? ERK stands for extracellular signal regulated kinase. Okay, so the E is for extracellular and signal. Okay, the R is then for regulated, and the K is for kinase. So we have these two different names for the same thing, basically, and this is what makes this pathway so complicated, because there are so many different names for the same thing. So mitogen activated protein kinase here is the MAPK name. Okay, and the extracellular signal regulated kinase, that is ERK here. Okay, or ERK as it's pronounced. Right, so we have in our title of this whole video, we've called it ERK rather than MAP kinase, and I would say that ERK is slightly more common now than MAP kinase, but both names are very common. Okay, so there are two forms of ERK. There is ERK1 and then there is ERK2. Okay, and again, we won't distinguish a different function between the two. Effectively, they do the same thing. Okay, right. So we'll colour in ERK here in orange. Okay, and when I say ERK, I now mean it's one of these two. It's either an ERK1 or it's an ERK2 enzyme. Okay, now, again, at the moment, ERK is sitting within the cytoplasm inactive. And what's now going to happen is it's going to be phosphorylated by the MEK enzyme. Okay, so the active MEK enzymes within the cytoplasm are now going to phosphorylate the ERK enzymes. Okay, and ERK's going to get phosphorylated at two places. One of these residues that it gets phosphorylated on is going to be a tyrosine residue, and the single letter code for a tyrosine residue is a Y. Okay, so this means tyrosine. And the other one it's going to be phosphorylated on is a threonine residue, and the single letter code for threonine is T. Okay, so that's why it's important that MEK enzymes are capable of capable of phosphorylating both tyrosine residues and also serine threonine residues. Okay, right, so this will now activate our mitogen activated protein kinase, or our ERK enzymes. Okay, so what's now going to happen is that the ERK enzyme is going to translocate into the nucleus, and it's then going to work on transcription factors. But before we come to that, I just want to talk about a little bit more nomenclature that you may come across. Okay, so the first is another naming system for the MEK enzymes. So you might, if you're unlucky enough, come across the MEK enzymes being referred to as the MAP kinase enzymes, kinase. Okay, so they might be referred to as the MAP kinase enzymes because they are the kinase which phosphorylates MAP kinase enzymes. So some people will call these the mitogen activated protein kinase, and then they'll stick another kinase on afterwards, and they'll abbreviate this to MAPKK. Some people will also abbreviate this to MAP, M-A-P, and then they'll put a 2K after it like that to mean that it's the two kinases there. Okay, right. This gets even more ridiculous with the other name for RAF kinase enzymes. So some people will abbreviate the RAF kinase enzymes to the MAP kinase enzymes, because they are the kinase enzymes which, remember, phosphorylate the mitogen activated protein kinase enzymes. Okay, so you might see RAF enzymes abbreviated to MAP3K or MAPKKK like that. Okay, generally people avoid that, firstly because of how ridiculous it is, and secondly because it reminds us of a horrible part of history. Right, okay, so we'll call it there for this video, and in the next video what we'll do is we'll continue on the story and look at what MAP kinase ERK enzymes are now going to do.